Today we are discussing the exact mechanical difference between the proton and the antiproton. Now, all physicists know is that the proton is a mirror image of the antiproton and that they have different charges. The proton has a +1 charge, and the antiproton has a minus 1 charge. Okay, so if they're close enough, they're going to attract each other, and then they both have spinning sacs. And is that an issue for you, sacs? Well, there are 4 indestructible particles, and if you can proceed as if there's a GP1, a ether medium for electromagnetic waves under pressure, then you can appreciate that the universe, okay, is a sac with matter and energy reflective edges. Only the universe sac can contain all the mass and energy in the universe, okay? All of that mass can never be compressed into a singularity. But I digress here. The issue is that has stumped physicists is what is the mechanical difference? What distinguishes it other than the charge? And the answer is that we are given that the proton, to me, it's a permeable sac. So just proceed as if the proton is a permeable sac that pulsates GP1 or ether particles in and out. Okay? Now, the medium for electromagnetic waves allows atomic level pulsations to harmonize into observable electromagnetic waves, okay? Whether it's a gravitational wave, okay? And a gravitational wave is similar to electromagnetic wave, but the gravitational wave depends on whether matter is heating up, okay? So when matter is heating up, the net harmonized compression bead of all the electromagnetic waves put out by the sun, okay? And the sun has been heating up from 10 degrees Kelvin for the entirety of its life and will continue to heat up for another 4 years. 5 billion years, okay? Now, as long as all the matter not all the matter, but most of the matter in our sun is heating up, it's going to generate gravity. When that matter starts cooling, dark energy is going to come out, okay? So the first thing is the conservation laws apply to gravity, conservation laws, okay? As you generate gravity, you store dark energy. And as you release dark energy, you store potential gravity, okay? So as matter heats up, gravity is generated. As matter cools down, anti-gravity is generated. And that's because when in my postulate, in my view of the grand unified theory of the cosmos, GP1s are net compressed into matter particles, and I view them as permeable sacs. So as GP1s get compressed from the medium of electromagnetic waves, okay, they have some bounce in the medium, pressure, that's called pressure, vacuum pressure. So physicists believe in vacuum pressures. There's a vacuum pressure, and when you heat up matter, you heat it up by imploding GP1s into the neutron permeable sacs, the proton permeable sacs, the electron permeable sacs, and the dark matter gets imploded into neutrino permeable sacs, as evidenced by neutrino oscillations that the neutrinos coming from the sun have different masses. So you can blow up the electron neutrino to different sizes, okay? And I say that's the result of putting GP1s inside those permeable sacs, and that's how you compress space into a lower volume. And then as the GP1s rush in, that's the force. That's the force that pushes our body to the center of the earth. That's the force. GP1s going from higher GP1 ether pressure away from the sun or away from the earth to the center of the sun is how the earth gets pushed towards the center of the sun. Okay? But I digress again, okay? What is the exact mechanical difference between the proton permeable sac and the anti-permeable sac? Okay? We are given that the proton has magnetic moments. What that means is it's like a little dynamo. Okay? So imagine a sac, a hovering sac, absorbing under high pressure GP1s and expelling under low pressure, under vacuum pressure, GP1s. If it net absorbs GP1s, it's going to make gravity, and if it net expels GP1s, the mass, all those nucleons overall. Okay, now okay, so we're viewing the proton permeable sac as a little dynamo, let's say, like the Earth, with a magnetic north pole and a magnetic south pole. Okay, so when you look down from the top, on a spinning proton sac, it's spinning clockwise. And when you look down on the north pole of a spinning antiproton sac, it's spinning counterclockwise. Now, an electron, if you look down on the North Pole, is going to be spinning counterclockwise. And a positron, if you look down on the North Pole of a positron. So that's the only mechanical difference. Okay, and it's consistent with what we're given. Okay, it's consistent. They're mirror images, but they have a different charge. Okay, so we can dispense with the idea that protons and antiprotons are pulled out of vacuum by energy. No, those are minted. They are minted. Okay, they're minted in the center of stars. Okay, so the neutronium in a neutron star, and a black hole just has more neutronium. that neutronium, it's going to warm up from the cosmic microwave background radiation from minus 100 trillion degrees Kelvin, and it's going to produce 18 or 36 or 72. So one solar mass of neutronium, when that neutronium warms up from 100 trillion Adoni Kelvin degrees below absolute zero, when it warms up to absolute zero, there's going to be maybe 18 solar masses, or it might be 36. I don't know the exact ratio. Okay, all I know is it's going to be more than one. Okay, so one solar mass of neutronium of a neutron star can be viewed like dehydrated onions. So when you add water to dehydrated onions, it's an 8-to-1 ratio. Okay, so when you add GP1s, when GP1s get imploded inside the embryonic neutron sacs in the neutronium of a black hole or of a neutron star, then you're going to get pristine new neutrons that are going to decay to pristine new hydrogen. Okay. But I digress. Okay. So the North Pole, okay, we're given that the proton has magnetic moments. So view it like a little dynamo, just as the Earth has a magnetic North Pole. The proton permeable sac has a magnetic North Pole. So all you got to do to convert a proton permeable sac to an anti-permeable sac is to flip the magnetic poles. You don't have to flip. You don't have to change the spin. The spin can stay the same, but you have to flip the magnetic poles, okay? So our sun's magnetic poles flip every million years, okay? Now the Earth's magnetic poles, no. Our sun's magnetic poles flip every 11 years. Now the Earth's magnetic poles flip every million years, okay? So that tells us that there's a cosmic flux lines, okay, uh, permeating like all of space, okay, or permeating the galaxy, the harmonized magnetic flux lines of our entire galaxy, okay. So now the proof. Now say, Adoni, what proof do you have that that protons can be converted to antiprotons and vice versa? Okay. Well, for the proof, we have to go to Sherlock Holmes. Okay. And what it was, if you eliminate all that is impossible, then whatever is left must be the truth. Okay, now physicists say that a type 1a supernova, which is a white dwarf, once it accumulates about 1.41 solar masses, it's going to blow up. And there's going to be, and everything is going to explode out, and there'll be no remnant in the center. Now, the physicists say that runaway carbon fusion is what powers the type 1a supernova, okay? But that's impossible, okay? Because the matter that makes up a white dwarf as it approaches 1.41 solar masses is going to be 20 million times the density of Earth. Okay. I think we're talking like 60 million times the density of diamond. Okay. So that's not the same as a gaseous carbon. And you can't get all the fusion energy that our sun is going to make in 15 billion years if it lived for 15 billion years or 10 billion years. You can't get that instantly from fusion. Fusion does not run away. Fusion for hydrogen that releases more energy does not run away. Okay? But if you mix 125 Earth masses of antimatter with 125 Earth masses of matter, you instantly get 1.5 to the 44th power joules. 1.5 to the 44th power joules, which is enough to power an average type 1a supernova, okay? So there you go. As a white dwarf approaches 1.41 solar masses, it's going to expand and contract, okay? Now, it's going to make antimatter in each expansion and contraction, and there's going to be a mixing of that antimatter as it expands and contracts, okay? Now, until it reaches escape velocity, it's just going to expand farther, okay? And then it's going to contract. It's going to expand farther, and it's going to contract, okay? Now, the same thing happens for other types of supernova. There's expansion and there's contraction. Now they say that there's a bounce. For the other supernovas, physicists say that the contraction bounces off and that powers the type 1a supernova. But that's not given. We are given, definitely. If you mix matter and antimatter, you're going to get instantly an explosion. So, for your consideration, is it more likely that when a supernova gets ready to explode, is it more likely that the expansion was caused by matter and antimatter mixing, but was insufficient to reach escape velocity for all the outer matter? Okay, so it compresses again, and during this compression, a lot of antimatter is created. And as it expands, that antimatter mixes with the matter, and you get a supernova explosion, okay? We know that if you mix matter and antimatter, you're going to explode. The more you mix, the bigger the explosion, okay? So that's a realistic way to explode, or a miraculous way, you know? So believe what you will, but consider which is more likely. Which is more likely? Matter mixing with antimatter, proton and antiproton changing under the compression pressure of a big star, or the compression pressure of a white dwarf as it approaches 1.41 solar masses. Talk more soon. Like if you like. You'll only hear it here. You'll come back. There'll be something new for you every day. Something new that will cancel out the fibs, that the embellished fibs that 3 million physicists around the world repeat every day. You'll learn the embellished fibs. Okay, talk more soon. Bye.